An apple fell on his head and changed everything. Not a golden apple, not a miracle, just a bruised piece of fruit dropping from a tree in a quiet English garden in 1666, while a plague locked the rest of England indoors. That single moment gave the world the universal law of gravitation. But what if it had not been Earth? What if Isaac Newton had been sitting not beneath an apple tree in Woolsthorpe, Lincolnshire, but beneath a thin Martian sky, red dust swirling around his powdered wig, no atmosphere to speak of, the sun a cold pale disk 140 million miles further away, and the apple falling slower than he had ever seen anything fall in his life? Welcome to the worst scientific crisis in human history. Isaac Newton arrives on Mars. He has his quill. He has his notebooks. He has the most terrifying mathematical brain ever produced by the human species. And absolutely everything he thinks he knows is about to be wrong. Let us be precise about what Newton brought with him. By 1666, this man had already invented calculus. Yes, he invented an entirely new branch of mathematics because existing mathematics was not good enough for his thinking. He had split white light into a spectrum with a prism. He was about to demolish 2,000 years of physics with a single equation. This was not a man who struggled with hard problems. Mars, however, does not care about credentials. The first thing Newton notices on Mars is the silence. Not peaceful silence. The silence of a world with 1% of Earth's atmospheric pressure. There is air on Mars, technically. Carbon dioxide mostly, as we now know. But in Newton's time, nobody knew what Mars was made of. He steps out. Somehow, in this hypothetical, he can breathe because the story collapses otherwise. And he immediately feels lighter. Not emotionally lighter, physically lighter. Mars has a gravitational pull of 3.72 meters per second squared. Earth's is 9.81. Newton weighs roughly 62 kilograms back in England. On Mars, he weighs the equivalent of about 23 kilograms. He is, by Earth standards, practically floating. He does not know this yet. He just knows something is deeply, profoundly wrong. He finds a rock. He drops it. It falls. But slowly, gracefully, almost dreamily, the way things fall in a dream where physics is being polite to you. Newton stares at it. He drops it again. Same thing. In his notebooks, and Newton's notebooks were obsessive, paranoid, meticulous documents filled with his private thoughts in a cipher he invented so no one could steal his ideas. He would have written something like, "The motion of bodies near the surface does not conform to any ratio I have previously established." Translation: What in God's name is happening? Here is the thing about Isaac Newton that most people miss. He was not just a genius. He was a genius who was also pathologically certain he was right. He had vicious, decades-long feuds with other scientists. He destroyed Gottfried Leibniz's reputation in a dispute over who invented calculus. He ran the Royal Mint and had counterfeiters hanged. He was not a man who accepted being confused quietly. On Mars, Isaac Newton would be confused, and that would make him dangerous. He starts measuring. This is what Newton does. He drops objects from different heights. He times their fall using a pendulum clock he brought with him, because of course he did. And the numbers do not lie, even when they are infuriating. Objects fall at a predictable rate, but the rate is wrong. It is too slow. It is roughly 38% of what he expected. He begins to suspect the problem is the planet. Now here is where it gets scientifically extraordinary. Newton's law of universal gravitation states that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. In simple English, bigger things pull harder and things farther apart pull weaker. Mars is smaller than Earth. Its mass is about 10.7% of Earth's mass. Its radius is about 53% of Earth's radius. When you run Newton's own equation, F equals g times m divided by r squared, with Martian values, you get exactly 3.72 meters per second squared. His law works perfectly on Mars. He just does not know it yet because he does not know Mars's mass or radius. He only has a pendulum clock, a quill, and an almost insane level of intelligence. He would figure it out. This is the astonishing thing. Given enough time and enough data, Newton would have derived the Martian gravitational constant from scratch. And in doing so, he would have realized something that would have shattered his worldview more completely than any theological crisis of his era. Which, given that he also secretly believed the Holy Trinity was a Vatican conspiracy, is saying something. He would have realized that gravity is not a fixed property of the universe. It depends on where you are. The Earth is not the standard. The Earth is just one data point. This is actually the moment in human intellectual history that took us centuries to fully absorb. Even after Newton published his Principia Mathematica in 1687, which his colleague Edmund Halley basically had to beg him to publish because Newton kept sitting on it, people still treated Earth as the natural baseline for everything. The universe was, in some psychological sense, Earth-shaped. Mars would have cured Newton of that delusion 300 years early. Albert Einstein would later complete the picture. In 1915, his general theory of relativity reframed gravity not as a force, but as a curvature in spacetime caused by mass. Spacetime for those who have never heard the word unpacked. Imagine the universe as a rubber sheet. Put a bowling ball on it, it warps the sheet. Smaller objects rolling nearby follow the curve. That curve is what we call gravity. Newton's law is not wrong. It is incomplete. It works brilliantly for most situations. We still use it to calculate satellite trajectories, to land spacecraft, to predict the paths of comets. But it breaks down at extreme scales near black holes and at velocities approaching the speed of light. Newton on Mars would not know about Einstein, but he would begin to sense the incompleteness. He would drop different objects, a rock, a feather, useless in this near vacuum, it just floats. A sealed glass jar of air he brought from England, now rattling gently in his hand. He would measure, calculate, remeasure. He would fill notebook after notebook with the obsessive, slightly unhinged energy of a man who cannot sleep because the universe is not behaving itself. And then one day, let us say 3 months in, when the Martian dust storms begin, he would look up. The sky on Mars during a dust storm turns from its usual pale pink-orange to a deep rust-colored brown. The sun dims to a weak orange smear. Visibility drops to near zero. In 2018, a dust storm of this type covered the entire planet and lasted for months, ultimately killing the Opportunity rover by blocking its solar panels. Newton would have no solar panels to kill, but he would have something worse. A complete inability to observe the stars? Newton needed the stars. His gravitational law was not just about apples and moons. It was about the orbits of planets. He had used the known orbital data of the planets, data collected painstakingly by astronomers like Tycho Brahe and Johannes Kepler, to verify that his inverse square law held across the entire solar system. Without the stars, without observational data, he would be blind. He would wait out the storm. According to research compiled by planetary scientist Bruce Jakosky of the University of Colorado, Martian dust storms can last from a few weeks to several months. Newton would wait. He was patient when he needed to be. He waited 20 years to publish the Principia. He could wait out a dust storm. And when the sky cleared, he would look up and see something that no human had ever seen with his level of mathematical preparation: the Earth. A pale blue dot, as Carl Sagan would famously describe it 300 years later. From Mars, Earth is visible to the naked eye. It appears as a bright blue-white point of light, distinctly colored, distinctly small. Newton would see it and feel, for perhaps the first time in his life, the visceral smallness of everything he had ever known. Every person he had ever met, every experiment he had ever run, every apple tree in England, all of it compressed into a single pixel of light in a Martian sky. He would pick up his quill, and he would do what Isaac Newton always did when confronted with something he did not understand. He would try to measure it. He would estimate Earth's distance from Mars, roughly 78 million kilometers at closest approach, 378 million at furthest. He would estimate Earth's apparent size in the sky. He would begin with the tools he had and the brain he had to triangulate Earth's mass relative to Mars, using the comparative gravitational acceleration he had measured on the Martian surface as his starting point. It would not be perfect. His instruments were not good enough. His data was too sparse. But the direction of the reasoning would be exactly right. And that is what makes Newton terrifying. Not that he always got the right answer, but that he almost always moved in exactly the right direction. The equation he might have scratched into that Martian notebook, imperfect and incomplete, would be the intellectual ancestor of the equations that eventually sent real spacecraft to Mars. The Mariner probes in the 1960s, the Viking landers in 1976, the Curiosity rover in 2012, the Perseverance rover in 2021, which is, as of this telling, still rolling across Jezero crater collecting rock samples. Newton's math, refined and extended through Einstein and beyond, is the reason those spacecraft arrived at the right place at the right time. The gravity of Mars calculated precisely enough to land a 1-ton rover on the surface of another planet from 480 million kilometers away. An apple fell on his head in 1666 and changed everything. On Mars, nothing fell on his head. The apples would have floated a little too gently, settled a little too slowly, bruised a little less dramatically against the red dust. But Isaac Newton would have watched them fall, and he would have asked why. And the answer, that the universe is not Earth-shaped, that gravity is local and relative and curving the very fabric of space, would have arrived eventually in those cramped, obsessive notebooks. An apple fell on his head and changed everything. On Mars, there were no apple trees, but the question remained exactly the same.